So thanks a lot. It's a great pleasure to be here, and I'd especially like to thank the organizers for re-inviting me when it was decided to have the thing online, so that I could actually come. So I'm going to talk about random growth models, and the one you see in front of you is a off-lattice Eden model. So these little balls are joining the this growing cluster of balls at rate 1, and so this is the type of growth that is just, you know, it's not as complicated as motion by mean curvature. It's just growth in the normal direction. But what we're interested in is the fluctuations of the boundary. These type of models are very, very common. So this could be a bacterial colony growing, or perhaps this is people not properly social distancing. And the thing that you are interested in when you're talking about models like epidemics is the actual growth rate. So because it's just normal growth, the thing, of course, on a large scale is going to be a ball, and it's growing at some rate, and that rate's usually called R0, and R0 is the important thing. But for us, the actual growth rate in the ball are the non-universal things. So if you had a model like this, the Eden model on a lattice, you would see it actually wasn't a ball, and the growth rate would be different. And those sort of non-universal quantities aren't exactly what we're interested in. We're interested in the fluctuations of the boundary. So, well, it's not moving. Just a sec. Okay, so if you're imaginative and you look in this direction that I've drawn here, the boundary actually looks like a function I'll call h. And that function h is growing at rate some ct. But the universal things, the things that are true in general in such models, is this t to the 1/3. So the boundary is actually got a fluctuation of size t to the 1/3. And on top of that, we have lateral fluctuations. So x is the lateral direction, which looks like this northwest southeast direction in this picture. And in that direction, you see these universal fluctuation processes, a of x, but they're living on a scale of t to the 2/3 in that direction. And it's these universal processes, these a of x, that we're interested in. Now, these processes actually depend on the initial condition, which was here just one seed in the middle. So here we're in the curved geometry. And what we'll be interested in is what these processes look like as functions of t and x for large time. And these are supposed to be extremely universal in such growth models. In fact, it's supposed to be true anytime you have a stable phase invading an unstable phase in 2 dimensions. So for example, if you had a noisy reaction diffusion equation on a 2-dimensional plane, then the boundaries of the stable regions would look like this also. It's roughly the same type of model. Or forest fires, things like that. They're all supposed to grow like this. So it's a very universal phenomenon. We're going to be very restricted to what we call here 1+1 dimensions. So in the picture, you see the 1+1 dimensions. So it's 2-dimensional. We think of one dimension as time and one dimension as space. Now, of course, in the model I've shown you, it's not so clear that the thing really is a function. So it's much easier to study models where there is actually a height function. So here's a model which is it's a directed model. So a directed model means that I've decided there's a height function, and now particles are falling from the sky and making little towers. So the blocks are falling as an independent Poisson process at every site, and they just pile up, and that pile up is the height function. So it's a height function over the one-dimensional integer lattice Z. If they were just piling up, it would be kind of trivial because they would be independent at each site. But what happens in this model is the blocks are sticky. So if a block falls on top of a tower, that's fine, it just adds 1, but it can also stick to the side of the next tower. So you see in this picture the block falling down and sticking to the side. So here's what it looks like on a large scale. This is this ballistic aggregation, and you can see the height function, though it's not exactly drawn there. I could draw it. The height function sort of looks like that. And now we're interested again in what type of height function does this look like. So it's roughly the same story. It's a constant times t plus t to the 1/3, but now we see a new process. And these processes I'll describe later. And this one's called A1. It's the area 1 process, whereas before we were supposed to see the area 2 process. The difference is that here in this picture, well, you can kind of tell, though I didn't show it starting, that it was starting from a flat interface. And so starting from a flat interface, we see a new process, A1 of x, whereas before in the curve geometry, we saw a process A of x. And what we're interested again is what is the general picture of these processes. Okay, now the two models I've shown you, the Eden model and ballistic aggregation, nothing of this sort is known at all. Maybe what's known for ballistic aggregation is that there exists some constant and the thing grows like CT. But the fluctuations are not known at all. There's a canonical model that the physicists have for such systems called the Piers Yu Jiang equation, which I think most of you have heard of. So here there's a height function, h of t and x, and now x is in R, so everything's in the continuum. And it's supposed to evolve according to this stochastic partial differential equation. And there's 3 main terms which have been put here, which are supposed to encapsulate the main effects of a model like the ballistic aggregation. So let's start from the right. So there's a forcing term, which here is given by space-time white noise. So if you don't know what space-time white noise is, you should just think that this is being given a random kick at every space-time point. If you did that, the interface would be extremely rough. So you add on a relaxation term, which you all recognize as a term like the heat equation, to compensate. And if you just had these 2 rightmost terms, you would have dth equals dx squared h plus c would be an infinite dimensional Ornstein-Uhlenbeck process. And this thing can actually be solved. It's a Gaussian process. And what you would see is that h looked roughly like a Brownian motion. And in fact, Brownian motions are invariant for that process. Now you add the key term, which is this lateral growth term. So where does this lateral growth term come from? Well, in these models, and you should now be thinking a little bit more of the Eden model, the growth is in the normal direction. The growth is outwards. And that's happening here too because of the sticky particles. And so the vertical component of the growth has to be a nonlinear function of the slope. Now, of course, if you look at this little picture I drew, the nonlinear function is something like the square root of 1 plus dxh squared. And I've just written the nonlinear function dxh squared. And that's because the amazing thing about this equation is it doesn't really matter what nonlinear function you put into it. Essentially, the only one is dxh squared. So any other nonlinear function would essentially give you the same thing. And the other amazing thing is that with this nonlinear term, Brownian motions are still invariant. So if you start from anything, however smooth, in an infinitesimal amount of time, the H looks like a locally Brownian version of your initial data. So this is an evolution, essentially, of Brownian-like things. And that's why it's so hard to make sense of the equation, because if you have a Brownian motion, dxh is just a white noise. The white noise is a perfectly well-defined distribution, but you're not allowed to square it. So the nonlinear term needs a very non-trivial renormalization to make sense of it. Okay. So of course that was made sense of by Martin Hare, but we're not so interested in making sense of this equation as understanding what happens on very large scales. And again, we have the same phenomenon. In the picture, I started from flat, so I would expect growth at a constant rate times t plus t to the 1/3 times this area 1 process, which lives on a scale of t to the 2/3. Now, another way to say that, to say exactly the same thing, is that I should put in this small parameter epsilon, and I want to rescale space, time, and the height with this 1, 2, 3 scaling. So the 1 refers to the epsilon to the 1/2, and then the 2 is the epsilon minus 1 of the space, and the 3 is the epsilon minus 3/2 of the t. And of course, if I do that, then there'll be an enormous constant. It'll make the CT enormous. It'll be of size epsilon minus 1. And I have to subtract that in order to see the fluctuations at the top. So it's exactly the same thing to say it has fluctuations of size t to the 1/3 on a spatial scale of t to the 2/3 as to say that we expect that this 1, 2, 3 rescaled height function, after subtracting some constant times epsilon minus 1 times t, should converge to some universal limit. And these are the universal fluctuations we hope to see. So all results about KPZ are results, or can be translated into results, saying that this thing has some limit, which is some non-trivial fluctuations. Now I want to compare that to the model without the nonlinearity. So if you don't have the nonlinearity, then it's just a linear stochastic PDE. It's solvable, as I said. It's Gaussian. It's called the Edwards-Wilkinson model, though in probability, we usually just call this the infinite dimensional Ornstein-Uhlenbeck process. And it would have a 1, 2, 4 scaling, the typical diffusive scaling. So instead of epsilon to the minus 3/2, you'd see epsilon to the minus 2. There'd be no gross movement of the interface. It would just fluctuate back and forth. And the lateral scale of fluctuations, well, we know that well, is t to the 1/2. The important thing to see here is that the fluctuations themselves would be of size t to the 1/4, not the t to the 1/2 we're used to. And that's just because we're a bit muddled up in our scaling. So the nonlinear term makes this thing super diffusive, not subdiffusive. Okay, so the t to the 1/4 has been replaced by a t to the 1/3 as the size of the fluctuations. All right. Now, for the KPZ equation, we actually have been able to calculate a few special one-point distributions. So what that means is we have a few special initial conditions for the KPZ equation. For example, the narrow wedge initial condition or the half Brownian initial condition. Now, what do those mean? So narrow wedge means to start KPZ with the log of a delta function. What does that mean? Well, KPZ actually turns out to be just the log of another stochastic partial differential equation, the multiplicative stochastic heat equation. I haven't written that here. But that equation, if you start it with the delta function, makes perfect sense. So starting that equation with a delta function and then taking logs is what we call narrow wedge. And you can think of, you take log of the solution of the heat equation, and log basically looks like minus x squared over t, and that's a narrow wedge. So that's why the physicists call that narrow wedge. Half Brownian means to start the stochastic heat equation with Brownian motion with e to a Brownian motion on one side, so for x positive, and with 0 on the other side for x negative. And so the log of that is minus infinity and a Brownian motion on the positive side. So it's minus infinity to the left. So these are some strange initial conditions. And when you start with those initial conditions, there's a bizarre generating function, e to the minus e to the h, which one is able to calculate the expectation of and see that it's given by some Fredholm determinant. The generating function is given to you. You don't have any choice about it. But this generating function is a nice generating function, and it actually does determine the distribution of H. The determinant is a Fredholm determinant of I minus a operator K, which is given by, it's an integral operator. So K is an integral kernel, and that integral kernel is some special integral kernel, which is calculated. It depends on the initial data, and of course, T, X, and R. I won't write them down. They're a little bit complicated. The key point is that all we know is one-point distributions for 2 or 3 special H0s. It's not known if there's formulas like this for other models. These formulas are extremely special, and they rely on finding related formulas in models like ASEP. I'll be describing these models in a second, which approximate the KPZ equation. And in those models, they rely on magic combinatorial formulas, which are extremely dependent on the initial conditions. So it's not known if these formulas are very general. Okay. So what we're going to talk about in this talk is a special discretization of KPZ called TASEP, for which we have general results. So let me describe TASEP. Okay. So TASEP is an evolution of height functions. And now the height functions are just simple random walk paths, which means they're functions over the integer lattice, which are only allowed to change by 1 from one integer to the next. So they only go up or down by 1. And that's called a simple random walk path. So I've drawn one of them here. And the model can also be coded as particles. So whenever there's an up, you can draw a particle in that position on the integer lattice. So here you see the coding of this height function by particles. So a particle means it goes up that time, and a hole means it goes down. And the rule of TASEP, so that's the state space. And the rule of TASEP is that particles are attempting jumps to the right at rate 1, and they're only allowed to jump if there's no particle in the way. That's the exclusion. So this is called the totally asymmetric simple exclusion process. Now you can see when a particle jumps to the right, if it's allowed to, just means that a little local max jumps to a local min. So the dynamics is just like this. A local max jumps to a local min, and then another local max jumps to a local min. And these are all doing this independently of all the other ones. Okay, so local maxes jump to local mins, local maxes jump to local mins. And that's the whole dynamics of TASEP. So that's the model TASEP, and I hope everybody understands what it is. It's very simple to state. You might wonder why I said it's a discretization of the KPZ equation. Well, the dynamics here is just the rate of change of the height function. Well, it changes by -2 whenever there's a local max. So I've written that as the indicator function of a local max. dt plus a martingale, plus d a martingale. And the martingale looks roughly like space-time white noise. The interesting thing is, if you look at this function, -2 times the indicator function of a local max, because of the discreteness, it can actually just be written as a half times the backwards gradient of h. So grad minus of h at x just means h of x minus h of x minus 1 times the forward difference, h of x plus 1 minus h of x minus 1 plus the discrete Laplacian of h. So this thing really does just look like a discretization of the KPZ equation. On the other hand, it is not true that this discretization converges to the KPZ equation in any sense. It's just a model sort of at the same level as the KPZ equation, a different one. If you want to converge the KPZ equation, you should allow local mins to jump to local maxes as well. And if you did this, and you did it in an asymmetric way so that there was just slightly more jumps down than there were up, and that difference was epsilon 1/2, then in the 1, 2, 4 scaling limit, it would converge the KPZ equation. And so that model is called the asymmetric simple exclusion process. And the way you get formulas for KPZ is to find formulas for the asymmetric exclusion process or some other discrete models which converge to KPZ, and then take limits of those formulas. Okay. So here's a picture of what happens if you start with the wedge initial data, which just means the black line. So it's just, that was the initial data for the TASEP, and you run it for a while, and the blue line is what you see. The red line is a parabola just for your eye. And you can see that the blue line is close to the parabola, and that you should think of that as the analog of the fluctuations of the original Eden model away from the ball. So we're interested in this universal process, basically, of the blue minus the red. Okay, so now I'm going to show you the results for TASEP. So we're interested in the results of the 1, 2, 3 rescaled TASEP. I'm going to state them like that, as limits as epsilon goes to 0. What happens to the one-dimensional distributions and then the multidimensional distributions. You can also think that there's a limiting model of TASEP under the 1, 2, 3 scaling, which we'll describe later. It's called the KPZ fixed point, and these are just formulas for the KPZ fixed point. So here's the simplest model. I'll state them starting with the simplest case, and the simplest case is starting with flat. So we start TASEP with a flat initial condition, and we're interested in the distribution function in the 1, 2, 3 scaling limit. Or as I said, you can just think that there's an asymptotic model, which is the 1, 2, 3 scaled version. So it's just htx, and you don't have to take a limit as epsilon goes to 0. And that gives you a function f of t and r. It doesn't depend on x, because we started with flat initial data, so the thing is spatially homogeneous. So we've got this function f of t and r, which is the distribution function at time t of the asymptotic model, the KPZ fixed point of htx less than or equal to r. So that function f, we take its second log derivative, and lo and behold, it satisfies KdV, the Korteweg-de Vries equation. So that's a little bit of a surprise. And the biggest surprise is this fellow d cubed, which we don't usually see in probability. KPZ is a theory in which the standard things we see in probability, like d squared, the generator of Brownian motion, end up being replaced by d cubes. Okay. So now I'll give you the analog of this result for general initial data. So if we have general initial data, well, first of all, we need to know that our initial height function rescales in the 1, 2, 3 limit to some asymptotic height function, which I'll call frac h0. Of course, there's no 3 here because it's just at the initial time. And now we look at the distribution function of the asymptotic model at space-time point t and x. And that's a function of f of t and r and x. And we take its second log derivative, phi. And it satisfies an equation called Kp, which is just the two-dimensional version of KdV. It's another integrable equation. It's just like KdV where you've added on a x variable. And in the first set of brackets, you actually see the KdV equation. So it's dr of the KdV stuff plus heat equals 0. Okay, so that's the Kp equation. And now we're interested in multidimensional distributions. We want to characterize the limit. And the characterization of the limit is not just done by one-point distributions, but we'd like to know multipoint distributions. So general initial data, and now we look at multipoint distributions. So we take a bunch of points t, xi, always one time multipoints. So one time multipoints, xi's, and we want this thing to be less than or equal to ri. So that's a function f of t and the x's and the r's, and there's n of them, and n is arbitrary. And these satisfy a matrix generalization of the Kp equation in variables which strangely are the sum of the r variables and the sum of the x variables. There's a matrix capital Q and its derivative little q, and they satisfy this matrix Kp equation, and then you take the trace of the q's, and that's the log derivative of the distribution function. Okay, so those are the main results. And if no one has any comments, I'm going to, well, there's the Kp equation. And the question is, why? So first of all, I just want to go back and say that's all the information we need. These f's, just like the finite dimensional distributions of Brownian motion, characterize Brownian motion, these multipoint distributions of H determine the asymptotic fluctuation process at a fixed time t. But we'll also see that actually the asymptotic fluctuation process is a Markov process. So knowing what it is at each fixed t is enough, and that determines the entire process. Okay, so let's go. So why on earth does this thing satisfy these equations that come from classic integrable systems? And the answer is we don't really have a physical derivation of this fact. They're derived by algebra. And it's not at all clear why this is happening. The KP equations and KdVs are equations which are classically derived from shallow water waves, but there's no connection between the classical derivation and our equation. And in fact, if you look at the initial data for our equation, which I haven't written, but which it's a bit complicated, so I won't write it out, but they're not too hard to derive. They simply have nothing to do with the types of initial data which were classically used in KP and KdV. But in fact, there's actually a deeper question. If you knew that these finite dimensional distributions satisfy a closed equation, it's not that hard to guess that it might be this equation, because the equation has to have a certain scaling invariance. And that scaling invariance forces equations of this nature. The deeper question is, why would the endpoint distribution satisfy a closed equation at all? We have no idea. If you look at the special cases I showed you before, starting with flat initial data and step initial data being this wedge, then one knows that in the flat case that the thing's stationary in space, and in the wedge case or the step case, one knows that after you subtract a parabola, it's stationary in space. And you can use that plus the self-similarity because of the t to the 1/3, t to the 2/3 scaling, and just posit that there'd be self-similar solutions of that form to KP, and it immediately reduces KP to the Panlevet-2 equation. And that's where the famous Tracy-Whittem distributions come from. They're just special self-similar self-similar forms of KP. Okay. Now, as I said before, it's not just the limiting fluctuations of TASEP and the 6 other models we can actually do this for. There's a limiting Markov process, HTX, which is called the KPZ fixed point. And the KPZ fixed point and TASEP, their transition probabilities are actually given by Fredholm determinants, which I'll describe in a second. So in a few minutes, I'll describe the Fredholm determinant formulas for the transition probabilities of TASEP and their limits. And the equations, the KdV and KP, actually come from basically differentiating these Fredholm determinants. You don't need to know much about Fredholm determinants in this whole business. You can just think of Fredholm determinants as just classical determinants, because the operators, all the operators involved are trace class operators. The trace class of an operator just being the sum of the absolute value of the eigenvalues. So these are compact operators, and the trace class means that they're very well approximated by finite dimensional versions of the operators. And the determinant is actually continuous on the trace class. So you're just fine pretending everything is just finite dimensional approximations, and the determinant just works exactly like the classical determinant. To derive the equations, all we're doing is we're following Tracy-Whittem in their proof that determinantal formulas can be rewritten as Panlevet-2 for the Gaussian unitary ensemble. And the main point is that if you have a determinant of I minus a operator k depending on a parameter r, and you differentiate the log, you get a trace. And that's the starting point of everything. So once you take the log derivative of the determinant, your interlinear objects trace, and now you just basically are differentiating trace and discovering by millions of integration by parts relations between very complicated strings of operators. Exactly the same method, because they were also given by determinants, shows that the log derivatives of the generating functions for the cases I showed you for KPZ also satisfy the KP equation, which is a huge mystery. This is true for a narrow wedge, and it's true for half Brownian. But the mystery is compounded by the fact that there's actually a Pfaffian formula for the generating function of the flat KPZ, which has not been proved. It's a conjectural formula of physicists. And we can check that it does not satisfy KP. So it's not terribly clear what's going on. But it's definitely clear that some of these formulas which are cropping up in KPZ are related to KP. Okay, so here's a big picture of the universality class of KPZ. So this is supposed to be a schematic picture containing the universe of models in the KPZ universality class. And there's a scaling, which is this 1, 2, 3 scaling, in which models are being sucked into this universal KPZ fixed point. And TASEP, which is over here on the left, is one of the models which is supposed to be sucked into the KPZ fixed point. And I wrote a little green line because we can prove it. And what's supposed to be true is that all sorts of other models, like ballistic aggregation, Eden models, phase boundaries of dynamic easing models, as long as there's a magnetic field, so there's a phase which is stable and an unstable phase, are supposed to be sucked into this universal KPZ fixed point. The universe has another fixed point, which is the Gaussian or Edwards-Wilkinson fixed point, and models which are symmetric, like phase boundaries of the dynamic easing model, without a magnetic field, where there's no phase which is stable versus an unstable phase. So the boundary between them is just fluctuating back and forth. Or in the language more of this program, you'd have a potential with two wells which are of equal depth in a reaction diffusion equation. Then these will be sucked into this Gaussian Edwards-Wilkinson fixed point, which would describe this fluctuating boundary, just fluctuating back and forth with Gaussian fluctuations. And it's got this 1, 2, 3 scaling. The two fixed points have different invariances. The Gaussian fixed point is actually invariant under flipping the sign of the height function, because there's no preference for one phase versus the other. And it's also invariant under sending time backwards. The KPZ fixed point, on the other hand, has what's called skew reflection invariance, which is that if you change the height function to minus the height function, you have to also at the same time change t to minus t, and then you recover the same process. In this picture, the only special role of the KPZ equation is that it's a heteroclinic orbit connecting the two universal fixed points. It's got this coupling parameter lambda, and in the strong coupling limit, lambda goes to infinity, it should go to the KPZ fixed point. And in the weak coupling limit, of course, as lambda goes to 0, it becomes the Edwards-Wilkinson model. The important thing to keep in mind is that the KPZ fixed point itself doesn't satisfy any kind of stochastic PDE. Okay, and I've also described down here in the little pink wedge SPD world, where we have models which are close to converging to the Edwards-Wilkinson fixed point. So for example, the weakly asymmetric simple exclusion process, where the asymmetry is taken to be very small so that you steer the model close to the Edwards-Wilkinson fixed point so that it converges actually to the KPZ equation, because you've held the nonlinearity to be order 1 in the scaling. And these type of things are well understood now by PDE techniques. Basically, Martin Hare's machine can prove that for essentially anything. But above this pink wedge, we're in a land where analytic techniques don't seem to work at all, and all we can do is algebra. Okay, so our main starting point is the following formula that we discovered 2 years ago for the TASEP transition probabilities. And hopefully I'll have time to give you some history about this formula in a few minutes. So we're going to start with initial condition with a finite number of peaks, just to make the formula simple. And we'd now like to know the probability that the height function at time t at a bunch of xi's is less than ai's. So this is given by some Fredholm determinant, as I said, and the important thing is the form of the kernel. So the kernel, as you can see, is the product of a bunch of operators, some of which are very simple. They're just e to the t over 2 grad minus. Well, that's just the solution of solving the equation dtu equals grad minus u, which I think everybody here can do. The q is just the transition probabilities of a geometric random walk jumping down. So that's simple also. And then there's these things, the important things are these r's. So there's an r for the initial condition called RIC, and there's an r for the final condition. And if you look, they're rather the same. So I'll just talk about the r for the final condition. And if you look, the key object in the r for the final condition is just a product of indicator functions and q's, which is nothing but the transition probabilities of the geometric walk forced to stay above the final condition. And in the initial condition, it's the same type of thing, but it's forced to stay below the initial condition. So just saying this again, this is the transition probability. This is an operator, and the operator, the UV element of the operator is the probability to start at U, to get to V, and stay above the final condition or below the initial condition. And then you've got these funny things which mediate, which is this Q to the S1 minus SM, which is actually an inverse power of Q, but these Q happens to be invertible. So this is also computable. So this is the formula. It's a very simple formula. And the important thing about this formula, and I'll show you where it came from, hopefully in a few minutes, is that it's very well adapted to taking limits, because these transition probabilities of the walk forced to stay above the final condition or below the initial condition are just going to converge in the limit to transition probabilities of Brownian motions forced to stay above the initial condition. So when you take the limit in the 1, 2, 3 asymptotics and you use the formula for Q inverse, the important object that needs to, the thing which is giving you a non-trivial limit is this e to the epsilon minus 3/2 t grad minus times q to the epsilon minus 3/2 t. Now, just informally, if I write this as e to the epsilon to minus 3/2 t times minus grad minus plus a half log of Q inverse, then expanding those things and realizing I'm on a lattice of size epsilon 1/2, one finds that this gives you the d cubed. And as I said, the transition probabilities converge to the transition probabilities of a Brownian motion staying below the initial or final condition. Okay, so in the limit, you get the transition probabilities of the KPZ fixed point. So the transition probabilities are completely defined by their finite dimensional distributions. And give me hold on a second.
Sorry, Jeremy, This is your few-minute warning.
Yeah, sorry about that.
Sorry about that.
I had a kid in here. Sorry, how many minute warning? Hello?
Well, sorry, let's say 4 minutes. We started a few minutes late.
Oh, 4 minutes. Wow. Okay. Wow. Okay. So the transition probabilities of the KBZ fixed point are given by their finite dimensional distributions, which are given by these Fredholm determinants again. And it's just the limit of the previous formula. But in the limit, you can see that the kernel is evolving just in this very simple way. It's just a base kernel, KH0, which is just given by probabilities of a Brownian motion to go from U1 to U2. Here it's written as hitting the initial data, and surrounded by this simple evolution equation involving d cubed. So one starts just with this hit operator, and then in the land of operators, the evolution is completely trivialized. So the Markov transition probabilities of this KPZ fixed point are themselves a completely integrable system. And this map is a continuous bijection from upper semi-continuous functions into the trace class, so everything makes perfect sense. Okay, so we know these transition probabilities completely. I'd like to just give you an example. So in the narrow wedge case, the initial height function is just 0 or minus infinity. So it's just, it doesn't look like a function. It's just this narrow wedge. And so the hit probability is just easy to compute. It's just you solve the heat equation, but then you have to stay above this, below this red line. And then you solve the heat equation for the rest of the time. And so the entire computation just gives you this area kernel immediately. And now, again, you look for a solution of KP of the form of this scaling form, and you get an ODE, and that ODE by the Riccati transformation gives you Panlet A2, and so this gives you the GUE distribution. In the flat case, it's similar, except instead of a projection, you get a reflection operator because you're using the reflection principle to do the calculation. So the scattering operator is the reflection operator, and then you get the GOE distribution by a very similar computation. Since I only have a minute, I just want to quickly summarize where these formulas came from. They're basically versions of Schutz's formula from 1997, which gave you n particle transition probabilities of TASEP via contour integrals. So Schutz's formula looks like this. So this is a formula for the n particle to n particle transition probabilities of TASEP. There are determinants full of contour integrals. And you should think of this formula as analogous to the Carlin-McGregor formula for the probability that a bunch of random walks or Brownian motions go from some points to some points without doing without intersecting each other, which is also given by determinants. But the problem with Schutz's formula is that it's extremely hard to take a n goes to infinity limit of this formula. In fact, the entire field of KPZ is basically the attempt to take the n goes to infinity limit of this formula. These formulas are actually very simple to derive. One just looks for a general solution for free particles and then the boundary conditions for the determinant. So the story is that Sasimoto discovered that Schutz's formula could be rewritten as a determinantal point process. And then the problem became to compute the correlation kernel of that determinantal point process. And the problem is the following problem. And I'll just finish with this problem. So the kernel of the point process is actually at the bottom of the page. It can be written as the sum over k of phi's and psi's. The psi's are actually given to you as shifted Charlier polynomials. Charlier polynomials are just the orthogonal polynomials with respect to the Poisson measure on Z plus. So you take these Charlier polynomials, and now you shift them by your initial data. And these initial data are the positions of the initial positions of the particles. And now you want to find biorthogonal pairs to them. And those are the phi's. And the problem with this thing, which is from 2005, is that no one has any idea how to solve such a problem to find the biorthogonal pairs. The only thing they could do is guess that the biorthogonal pairs were probably about the same as the size. And that works exactly if you have n particles evenly spaced in a block. And then the size and the phi's are basically the same thing. And that's why one could solve the narrow wedge and the flat case by taking limits of particle, no particle, particle, no particle. And that was the only case known. So the main tool that we have is that we are able to solve this problem in complete generality. The phi's are actually essentially just the probabilities that a geometric random walk hits the epigraph of the initial particle distributions at time k. And this is actually once you guess the solution, which took 12 years, it's not particularly difficult to prove. It's just that there was no easy way to guess it. And it's a completely general result. It works for any initial data. And then taking the limit, one gets this KPZ fixed point. So I'll stop there.